All right, let's continue talking about volumes of solids. Here's a nice warm-up example here. Let's set up an integral for the volume of the solid formed if I take the area between y equals root x, y equals 6 minus x, and x equals 0, this little triangular looking shape. And we're going to revolve that around the y-axis to get a three-dimensional solid. This is a whole three-dimensional thing. And so to find the volume of that, we were talking about in the previous video, you can imagine slicing this horizontally. Every slice is going to be a thin horizontal disk. But, and we know the formula, right? Our general formula for the disk method is pi times the radius squared times the thickness, which would be dy in this case. The radius of this disk would be the distance from the y-axis to this line. The radius of this disk down here, however, would be the distance from the y-axis to the square root function. So the first observation you would want to make here is that these disks are bounded by two different curves. And so the only way to do it, just like we've seen with area, you would have to break this up into two separate volume integrals. The intersection point for these two lines was 4, 2. Remember, the thickness is dy, so these are going to be dy integrals. The first integral is going to go from 0 to 2. That's the bottom half of this shape, where the radius is y equals root x, also known as x equals y squared. So pi r squared, right, this is my r squared. And then for the top half, I want to integrate from y equals 2 to y equals 6, where my radius is the distance from the y-axis to y equals 6 minus x, also known as x equals 6 minus y. Okay, we're not going to work that out. Now, that's not too terrible, but would there be a way we could find this volume without doing two integrals? And the answer is yes. But what we have to do is think about a new shape here. If I, instead of using horizontal cross sections, let's start with like just area. If I took this area and I put a vertical rectangle in there, what happens if I take just this rectangle and I revolve it around the y-axis? If I take this thin vertical rectangle, if I revolve that around the y-axis, I'm going to generate a tall, what looks like a washer, except there's an infinitely thin gap here, right? You got a big hole here, but it's got legitimate height here, but infinitely thin here. Almost like, you know, the cardboard in a roll of toilet paper or a paper towels, the little cardboard thing, it has a little thickness to it and it has some height, okay? And we call that a shell. That's not a washer. Washers have infinitely thin height to them, right? This one has some significant height, just a very thin thickness at the top. Those are called shells. Now, every vertical slice here is going to generate a shell of varying heights, right, and varying radii. So same idea as we've been pursuing. If you can find a formula for the volume of one of those shells, the integral will do the job of adding up all of the shells throughout that region. Now, the volume of one of those thin shells, if you can imagine, like, okay, imagine this is a piece of cardboard. If you cut it right through here and unravel it, you're just going to see a thin rectangular slab. So the volume of a shell is like finding the volume of a rectangular slab, where this would be the height. Okay, this dimension would be the height. The thickness in this case would be a small increment of x. This is the x-axis. That thickness right there is a small dx, but it could be dy, as we'll see. This length right here is like if you unravel it, that's like the circumference of the top. And the formula for circumference is 2 pi times the radius. The idea is we're going to take a vertical cross-section at some random x value. So our radius, if you're revolving around the y-axis, your radius is going to be x in this case. But in general, the volume of your shells is going to be 2 pi times the shell radius, in this case it's x, times the shell height, times the shell thickness, which is going to be either dx or dy. This is a new method, the shell method. Again, for us, our radius was x. The shell height, going back to your picture, whoops, your shell height, just like when you do area, this height right here is top minus bottom, 6 minus x minus root x. So this is the shell radius, this is the radius, and this, all of this right here is my height. And okay, we won't evaluate this, but certainly this would be easier than trying to do the 2 integrals we had to do for if we were doing the disk method. Just like the disk and the washer method, you can use the shell method if you have your solid rotated about different lines other than the x and y axis. Here I'm going to rotate that same region around the line, the vertical line x equals 4, which is a line right through that point of intersection. And so if I rotate that, I get this solid here. I'm going to still get shells if I do vertical cross sections. This time they're rotated around over here. Remember that x is the distance from the y-axis. So this random cross-section right here, this distance is x, but the radius is this distance, right? And this total distance here is 4. So in this case, my shell radius is going to be 4 minus x gives me the radius. My shell height is still the difference between 6 minus x and root x. Thickness is still dx, and I'd be integrating from 0 to 4. Let's look at another one. Find the volume when the region between y equals sine of x squared and y equals 0 on the interval from 0 to the square root of pi is revolved around the y-axis. The graph of y equals sine of x squared kind of makes sense. It would look similar to a sine graph, probably not exactly the same. But notice if I plug in the square root of pi, I get this, and I square it, I get sine of pi, which is 0. And when x is 0, it's 0. So it starts at 0, and by the time it's at the square root of pi, it's also 0. It's probably going to look very similar to a sine, one arc of the sine graph. So if I take this region and revolve it around the y-axis to get a 3-dimensional solid, you might be thinking, hey, okay, the shell method's neat, but I kind of like the disk and washer method. Well, you would have a problem here, because if you think about, if you were going to do the washer method, you would want to use horizontal cross sections, right? You would slice it this way, and you would have a problem because what is this and this are the same function, right? So you'd have a problem describing it that way. So here you pretty much have to use the shell method. You want to have vertical cross sections because this height is just going to be given by this minus 0. It's just the sine of x squared. Okay. Yeah, so that was this note here. If you try to use washers, you would have to try to solve y equals sine of x squared for x. And that would be really yucky. But if you do it with the shell method, our general formula is 2 pi times the shell radius. Once again, if you're revolving around the y-axis, your shell radius is just going to be x, the distance from here to a random cross-section. My shell height is sine of x squared. The thickness is dx. And this is we were practicing u substitution recently. This would be a great time to use u substitution. If you let u equal x squared, du is 2x dx. We have an x dx, so if we do the wishing method, I would wish for a 2 to get my 2x, compensate with a 1/2. The 2x and the dx together become du. I have sine of u, and then I have 2 pi times 1/2, which is going to turn into just pi. And so I end up with the integral of sine of u, which is negative cosine of u. We talked about switching the limits of integration. I'm going to just change it back and plug in my x squared and use my original limits. Plugging in, you get negative cosine of pi minus negative cosine of 0. Cosine of pi is -1, so I have negative of -1, 2. Well, no, that's 1 plus 1, so I get 2 pi is my volume. One more. And if you want, this might be a good time for practice. Pause the video, sketch out the region, and see if you can decide, set up a volume formula for if you rotate this area around the x-axis. Okay. So, my region, y equals 8x, y equals 16 is a horizontal line, y equals x squared. The only region bounded by all three of those, there would be another region up here if you kept going. Usually you would take the one closest to the origin. So let's just go with that. Let's assume this was the region we wanted right here. Okay, so if I take this region, now here's one question I get asked all the time is, how do I know if it's better to use a disc washer method or a shell method? And the answer is this. Before you even revolve it, so let's not look at this yet. If you were setting up an integral for the area of this region, would it be better to use vertical rectangles or horizontal rectangles? Hopefully you can see vertical rectangles would not be the best because you have a different top function, right? Every vertical rectangle hits the parabola on the bottom, but it depends on where you are for what your top function is. So it would be much better to use horizontal cross sections because you'll always be bounded between the same two functions throughout the region. So here's what's true. If you know that it would be better to use horizontal cross sections if you were doing area, then no matter how you revolve this region, whether you revolve it around the y-axis or the x-axis, it would be better to stick with horizontal cross sections. Okay. So the way I've drawn it here is to show you that if you did vertical cross sections to get washers, you could do it that way, but you would have to break it up into two separate parts, right? Because this would be your dividing line right here, right at x equals 2. So we're not even going to do that. Instead, you could set it up with horizontal cross section. So if you take a horizontal rectangle and revolve it around the x-axis, that will sweep out a thin shell. So we have a shell. This time our shells are lying on their side, aren't they? So my general formula for the shell is 2 pi times the shell radius, shell height, shell thickness. If you're revolving around the x-axis and we're talking about a random horizontal cross section, then the radius is just y. It's at some random y value. The height is now like when we do area, it's right minus left. It has to be in terms of y. So this was y equals x squared, also known as x equals root y. This is y equals 8x, also known as x equals y over 8. That's why I have that there, dy. And you would integrate, your smallest shell is going to happen when y is 0, and your highest one is going to happen when y is 16. This is 416 is your y value. Okay. Lots of practice. You should be doing lots of practice problems, whether you get assigned them for homework or not. Setting up volume formulas and deciding whether you should be doing a disk or washer method or the shell method. It's the only way you're going to get better.